All right, hello Calc 3 and welcome to the first video lecture for this course. We're going to be covering section 11.3 today, which talks about polar coordinates. Before I begin the lecture, I do want to apologize for any weird sound quality that might come through. I did order a mic that should prevent my pen from making a bunch of noise on my computer screen, but it won't be here until Thursday. So until then, you're just going to have to bear with me. We do have two goals for today. The first goal is to review how to represent points in the plane using polar coordinates, and the second goal is to convert between rectangular or Cartesian coordinates and polar coordinates. So let's begin by reviewing polar coordinates. I assume that most of you are quite familiar with polar coordinates from the end of Calc 2, but I will pretend as if you are not, for those of you who might not be familiar with polar coordinates. So the basic idea for polar coordinates is actually going to begin by referencing the method that we typically use to plot points in the plane. Since you were in most likely middle school, you've been plotting points in the plane with a coordinate system that is called the Cartesian coordinate system. And with the Cartesian coordinate system, points are given by ordered pairs, which we typically denote as xy, where x represents the location of the point along the x-axis, and likewise y represents the location of the point along the y-axis. So let's draw a picture for this. Again, you're probably quite familiar with this system of plotting, but that's okay. It's okay to think about these things and exactly what's going on, and it'll lead into polar coordinates nicely. So here we have a picture of the plane. And let's say we have a point here that's going to be called xy. It's represented by that ordered pair. Then to write down the ordered pair for this point, we're going to count how many spaces we go to the right. In this case, it's 2. And then count how many spaces we go up to get to the point. So in this case, we have x is equal to 2. And y is equal to 3, as of course you know when you look at the point inside of the plane as I've drawn it. So this is one way to specify what points we're talking about in the plane. If I want to tell somebody else exactly what location I'm talking about in the plane, it suffices for me to tell them where that point is in location to the x-axis and where that point is in location to the y-axis. But this is not the only way to specify what points I'm talking about in the plane. And one other way, although there are a bunch of different ways, one other way to talk about what point I'm talking about is called the polar coordinate system, which I will underline because this is more of a new concept. And in the polar coordinate system, points are still represented by ordered pairs. But the ordered pairs are typically denoted r theta. And in this case, r is the distance of the point from the origin, and theta is the angle between the ray that connects the origin and the point and the x-axis. So theta is going to be the angle between that ray and the x-axis. So just like the Cartesian coordinates, I'm going to draw a quick picture here. So let's say I'm given the coordinates, let's say 2 pi over 4. Then to plot this point, you can think about starting at the origin and immediately rotating pi over 4 radians counterclockwise. So think about yourself standing at the origin, and then you're going to rotate pi over 4 radians counterclockwise. So now you're facing this direction up here. And then the 2 in our ordered pair up here is going to tell us how far we're going to walk from the origin. So after I'm facing the correct direction, I'm now going to walk out 2 units, which should put me right about here. So the point that we'd be talking about is right here on the plane. So immediately after this example, we should specify some unique characteristics of plotting points in polar coordinates that are different from plotting points with Cartesian coordinates. So the first interesting thing to note is that polar coordinates, or maybe it's better to say a representation of a point in polar coordinates, unlike Cartesian coordinates, are not unique. Meaning that if you give me a particular point in the plane, I can represent that point using polar coordinates in multiple different ways. So let me give some examples. So consider the ordered pair 2 and 3 pi over 4, and then the ordered pair 2 and 11 pi over 4. These represent the same point. So to see that, if we draw a plane, and I want to plot 3 pi over 4 first, I'm going to start at the origin and rotate 3 pi over 4, which should put me over here. And now I'm going to walk out 2 units, which should put me about here. So that's plotting the first ordered pair. Now let's move on to the second ordered pair. I'm going to start, actually I think I'm going to draw another plane for the second ordered pair just so things don't get too cluttered. So again, I'm going to rotate about the origin, but this time theta is 11 pi over 4. So I'm actually going to rotate all the way back to the beginning using 8 pi over 4, and then go another 3 pi over 4 to end up at the same place. So I'm still going to be facing the same direction, and now I'm going to walk out 2 units in that direction. And lo and behold, we end up with the same point. So in fact, if you take any representation for a point where you have the representation is equal to r theta, and you add 2 pi to the theta, you're going to end up with the same point in polar coordinates. Whoops. Also, we can consider these 2 ordered pairs. How about 3 pi over 4 and negative 7 pi over 4. And again, these are going to end up being the same point in the plane. So we've already plotted 2 3 pi over 4 up here, so I'm only going to bother plotting the second point. So we're going to start at the origin, and we're going to rotate 7 pi over 4 radians, which should put me here. And then because r is negative, it means that I'm actually going to walk backwards. So I'm going to walk in the opposite direction of theta. So now I'm going to walk back this direction 2 units, and lo and behold, again, I get the same kind of point. So again, we see that we can represent points with polar coordinates in the plane in multiple different ways, either by adding multiples of 2 pi to theta, or by adding an odd multiple of pi and then making r negative. These are all representations of the same point. Okay, so let's move on to a couple of different examples using polar coordinates. The first example will be to give an equation in polar form of the circle. Maybe I should write for the circle. For the circle centered at the origin of radius 3. And there will actually be 2 different equations that will work here. So the first equation that will work is just r equals 3. And what this means is that we're going to talk about all points in the plane that are 3 units in distance from the origin. So all points that are 3 units from the origin are going to satisfy the equation r equals 3. But we could also write the equation r equals minus 3, which would also be all points that are minus 3 units from the origin. And any point that is 3 units from the origin, when viewed with the right theta, will also be minus 3 units from the origin in some other direction. And now a second example. We're going to graph the set of points that satisfy the following conditions that I'll write down here. So we want r to be between 1 and 2, and we want theta to be between 0 and pi over 2. So again, I will draw a plane. And the fact that r has to be between 1 and 2 means that all of the points are between 1 and 2 units from the origin. The fact that theta has to be between 0 and pi over 2 means that the points will be in quadrant 1. Okay, so I can draw part of the circle of radius 1 centered at the origin, and then part of the circle of radius 2 centered at the origin. And the points that satisfy both of these expressions here, or both of the conditions, are going to be the points that are between these 2 circles, because all of these points are going to be between 1 and 2 units away from the origin, and they're also going to be within the first quadrant, meaning that theta is between 0 and pi over 2. And now we can move on to the last section for the lecture for section 11.3. And we're going to talk about relating Cartesian and polar coordinates. It seems that often when this material is taught to students, students are given a couple of formulas that they are intended to manipulate to go back and forth between equations in Cartesian coordinates and polar coordinates without really giving a justification for why those equations are what they are. And so I want to give a little bit of a justification for why the equations exist, why they make sense. And to do that, let's just put an arbitrary point in the plane. So I'm going to call the point P, and I'll put it up here. And we know that P can be represented by the ordered pair xy in Cartesian coordinates. It can also be represented as r theta in polar coordinates. And if P is represented as xy in Cartesian coordinates, it means that the length of this line segment here, which I've just drawn in blue, is going to be x. And the length of this line segment is going to be y. And the length of this line segment here is going to be r, because that represents the distance from the origin to the point. And finally, the angle here is going to be theta. So now I have a geometrical interpretation of the values that are showing up inside of the ordered pairs that represent P. And we can find relations between these different values that are showing up inside of our picture here. So the triangle in the picture is a right triangle. So by the Pythagorean theorem, we can write down that r squared has to equal x squared plus y squared. And we can also use properties of the trig functions to write down that the tangent of the angle theta is equal to y over x, since the tangent of theta is equal to the length of the opposite side, which is y, over the length of the adjacent side, which is x. We also have that cosine theta is equal to x over r, and we have that sine of theta is equal to y over r. So if you need to pause the video for a second and see why these equations are true, I encourage you to do so. But they really do just follow from some basic geometrical principles. So we can conclude just from this little sketch here. So the point, say we have a point represented by the ordered pair r theta in polar coordinates, equals the point, I should write that in red, equals the point r cosine theta, r sine theta, where this ordered pair is in polar coordinates and this ordered pair is in Cartesian coordinates. So right away we have a way to relate Cartesian and polar coordinates. And now I will present the 4 equations that you can use to convert Cartesian equations to polar equations and polar equations to Cartesian equations. So to convert between Cartesian and polar equations, we use the following 4 relations. This is probably the most important thing to take away from this video. So I'll just list them here. So r squared is equal to x squared plus y squared. X is equal to r times cosine theta. Y is equal to r times sine theta. And tangent theta is equal to y over x. Also, I just realized when I was writing this that in the lecture notes I posted online, there is an error in 3 here, so watch out for that when you're using the lecture notes that are posted online. And finally, I'm going to give an example where we convert between a polar equation and an equivalent Cartesian equation. So we want to convert the polar equation to an equivalent Cartesian equation, and then we're going to graph. And the polar equation that we're given is r is equal to 4 divided by 2 cosine theta minus sine theta. So to convert this polar equation to an equivalent Cartesian equation, we're going to use the relations that I've written up here. So the first thing to do is to multiply both sides by 2 cosine theta minus sine theta. And now we can distribute the r through the 2 cosine theta minus sine theta. And we get 2r cosine theta minus r sine theta is equal to 4. And now we can use equation 2 and equation 3 to substitute an x and a y into this equation here. So this implies that 2 times x minus y is equal to 4. And now we can make this look a little bit nicer and write that y is equal to 2x minus 4. And this equation now looks super familiar. So this is a line with slope equal to 2 and y-intercept equal to minus 4. And we can certainly graph a line that looks like this. Okay, so I know that my line goes through the point minus 4. That should be down here. And it has a slope of 2, so it's going to go through this point. And now I can just draw a line through these 2 points. And this ends up being a graph of the polar equation up here inside of the plane. So if I gave you this polar equation and said graph this in the plane, you would probably give me a strange look, because it looks like it'd be pretty difficult to do. But after we changed it into an equivalent Cartesian equation, graphing the equation wasn't too hard anymore. It ended up just being a line. Okay, so that ends the material for section 11.3. You can begin working on homework. I should have it uploaded by Monday the 11th.